This week we're going to be learning about reactivity of elements on the periodic table and how the electrons in the outermost energy level, or their valence electrons, will determine that reactivity. So to start out, we need to know what reactivity means. It means something similar to what it sounds like. It means that a chemical reaction can happen, and something is considered more reactive if it is easier for it to have a chemical reaction with another element. So a simple definition here for reactivity could be the energy that is required to exchange or share electrons with another atom. So if you don't require very much energy, then it's easier for you to react. That would make an element more reactive. Some elements are so reactive that we'll actually see explosions. And so if a metal, for example, is the correct amount of very high reactivity, you might see it become explosive even when it's in contact with water. So then other elements will react, but these might happen so slowly that you have to add a lot of heat to it and stir it for a long time for the reaction to actually occur. So just before we really look at why, it's good to know that metals are more reactive when it's easier to get rid of their electrons, because metals are usually forming positive ions, and that's because they have less valence electrons and they want their valence shell to be empty. Non-metals are usually more reactive when it's easier to gain electrons from other elements to be able to fill up their valence shell, and this is because they have more valence electrons. They're closer to having that 8 valence filled shell. So they usually are, if it's easier for them to gain electrons, they're more reactive. Okay, so it's important to memorize some of this information to be able to explain the trends of the periodic table. So it's important to know the number of valence electrons that each column on the periodic table has. So the left two columns have 1 and 2 valence electrons each, and then we kind of skip over the transition elements, or the D block here, and we get to the P section of the periodic table. We've got 3 valence, 4, 5, 6, 7, and 8. And remember, 8 is filled, so these elements right here already have a filled shell and they don't become ions. Okay, so when we look at the different charges, depending on the number of valence electrons, will tell you what the oxidation state or the charge of the typical ion that is formed by that element would be. So anything in this column would have a +1 charge because it started out with 1 valence electron. That's very close to 0, so it's very easy for it to just lose that electron and empty out its shell and get a +1 charge. And the elements in the middle, we cut those out because they can have more than 1 charge, so we kind of ignore those for now. But each of the main columns, group 1, group 2, group 3, 4, 5, 6, 7, and 8, each of these has a pretty consistent charge that its ion would have, and so it's important to be able to know what charge an element would have based on what column it's in. So that's highly recommended that you memorize that. And then the group names are really important. So sometimes you would see a question that says, how come an alkali metal reacts really easily with a halogen? If you don't know what an alkali metal or a halogen is, that would make that question very difficult. But if you do know what they are, you'll know that alkali metals get a +1 charge when they're an ion, and halogens get a -1 charge when they're an ion. And so +1 and -1, it's the same value of the charge, but they're opposite, and opposites attract. So if we know the names and we know the charges, then it would make more sense when we read that question. Okay, so remember, each column has a certain oxidation state or charge that the ions would typically form, and we need to remember that, their valence electrons and the names of the groups. Okay. We call the right column noble gases mainly just because they're very stable, which is kind of like the word noble. Okay, so when elements react, there is an exchange of electrons, and that's why we're talking about electrons in the first place. All chemical reactions occur because of changing electrons with another atom, or sharing electrons with another atom. We're going to learn all about that in the near future. So let's look at this lithium atom. Lithium has one valence electron, so it only has one on its outside ring, so it's more likely to get rid of it. And here in this picture we see it donating it to this element over here. This is fluorine. Fluorine has 7 valence electrons and it only needs to get one more to be filled up. So when lithium gives fluorine its electron, then lithium becomes a +1 charge and fluorine becomes a -1 charge, and they're attracted to each other because of the opposite charges. And this will have an empty shell, this will have a full shell. So it's important to know that if the valence electrons are really close to the nucleus, so only the second energy level, for example, it's a lot harder to lose that electron because the nucleus is positively charged, the electrons are negative, so they're attracted to each other. And the closer the electrons are to the nucleus, the more that attraction is actually holding on to that electron. The opposite is true for elements that tend to gain electrons, like fluorine. If the electrons are very close to the nucleus, that nucleus is holding those electrons really tightly, but it also has more attraction to be able to take that electron from lithium because its nucleus is so close to its valence shell. Okay, so that's basically what these up here are saying. Now when we get to bigger atoms with more valence shells, or more electron shells, like this one right here is a potassium ion. It's kind of hard to see, it only has 1 valence electron. And chlorine has 7, so same situation, but now we have the 4th energy level and the 3rd energy level. These are a little bit further out from the nucleus, so the attraction from that nucleus is not as strong. It's a little bit easier for the potassium to get rid of an electron because its nucleus isn't holding onto it so tight. And it's a little bit less easy for chlorine to gain that electron because its nucleus can't pull as hard on the electron from the other atom. So there's advantages in both situations. The advantage with the bigger atom is for the metal, the positively charged ion, to get rid of its electron. And for a smaller atom, the advantage is for the nonmetal, the negatively charged ion, to gain that electron. Let's just review some of the periodic trends. Remember that all of the elements on this side past this line right here are nonmetals. These all tend to gain electrons, and that's because they are very electronegative, meaning they pull strongly on electrons, and they have a very high ionization energy, meaning that it's really, really difficult to remove electrons from them. They also have a really high electron affinity. That means their desire to gain electrons. So all of these elements, basically their trends will show you that they're going to gain electrons, unless if they're in this column. These already have 8 valence, so they don't need to gain any. When you look at this side, everything to the left of these orange elements is called a metal. And the further we go to the left, the more metallic character it has. So that means that it has a lower ionization energy, meaning it's easier for it to become a positive ion and lose those electrons. It doesn't really have much of an electron affinity, so that means that it's not very likely to gain an electron. But we also notice here, we've got this one atomic radius. The elements to the bottom left are the biggest elements on the periodic table. And this is because they have a lot of valence electron shells, and they have not valence electron shells, they have a lot of energy levels of electrons. And they have very few valence electrons, so their nucleus is not as tight, or is not pulling as tightly on the valence electrons because it's, there are very few of them. All right. So if we wanted to look at reactivity, all of those trends will help us to understand the reactivity of metals and nonmetals. So there is a specific trend for metals, and basically, remember, our metals are everything to the left of this little stair step over here. So all of these elements in the bottom left, you have the most reactive metals. So the ones that would be more likely to be explosive would be like cesium, francium, barium, radon. All of these are very reactive metals. Okay, this is because they have less valence electrons, so they have less things that they need to give away. So that makes it a little bit easier. They have a larger electron shell, so they're further away from the nucleus, they're easier to get rid of. So when it's easier to remove those valence electrons, that means it's more reactive. Now the opposite trend is true with our nonmetals, just like we talked about in the beginning. The more reactive nonmetals are to the top right. And this is because they have more valence electrons, so they're closer to getting to 8, so it's the desire to get that last electron is even stronger. They're more reactive because they have a smaller shell of electrons, so that means that the nucleus is really close to the outer shell, and so that nucleus can attract electrons from outside atoms much easier. And since it's got the stronger ability to fill its valence shell, that makes it more reactive. In a moment we're going to look at some example problems, but I'm not going to have time in this video segment, so I'll start the next one. So make sure if you're wanting to fill in some of the information on the back of your periodic table information graphic organizer, there were several questions, and these are important for your notes quiz that's coming up. So I'll get to that in the next video.